gonna get this tie-dye one some rack stuff too. Yeah. I'm making amends because what the hell are these sleeves?
I like to do the thing.
Are you telling me you don't cuff your sleeves already?
No.
It's just like choking me up. Like I need amends to loose.
But I might need a large, yeah.
Loose it like I'm wearing a muscle shirt. Like.
Okay. I'm rearranging them. So that Ari and Nori will be on the bottom with Sam. And then we will all go.
Again, I'm not saying that it's great, but I could pass for time if we put me right before.
Yes.
I can keep going. I'll just keep going.
Keep talking.
Are you gonna go back right now? I think so.
Okay, Nora, I'll move your stuff to the bottom.
She's already on the bottom.
Okay.
Wonderful. We might go back and get it.
Don't worry about it. It's fine.
But his phone's not responding though. I think we're thinking his phone is either.
I don't think Sam is dead.
I don't think
He's not dead.
Knowing Sam, he fucking
It's like a cockroach.
his phone died and his alarm went waking him up.
Yeah.
But that's not even losing the point though, because if his alarms aren't going off, this man depends on his alarms.
Why don't we?
I mean, who's responsible for Sam? You?
No, but let's.
I think we should do his final presentation later, and he'll have his very own.
Yeah, so.
Yeah, wonderful.
Because then you'll miss ours.
Okay, could you put it behind Tim's as well?
Yeah.
I'll move it behind Tim.
Yeah.
Relax, Nora. You got the nice chair.
The nice comfy chair.
Okay, I put his thing behind Tim's as well.
2 pillows just to make sure it's extra soft. Good.
Okay, so now we'll move Ari and Riz back to where they were.
Okay, let me share my screen.
Okay. I think who's going first? Sarah.
What, me?
I think because they got all jumbled.
Really? I don't see them. I don't see the jumble.
Yeah, I see the jumble.
Come on, share my screen. Come on. We don't go first, but I'm not first in line.
No one's gonna connect to the webcam.
It's kind of. Oh, I was going to, but then people were like, no.
Okay.
Unless you want to.
I mean, it doesn't matter to me.
I don't.
Go ahead. Okay. Ari.
Okay.
I have to reconnect to the office.
Hey, Freddie, can you also
Really? I didn't watch you last time.
Yeah, I can. Oh no, you're right. I'm surprised.
Oh, no, that's for audio. Where's video?
No, it's fine. I see it.
Oh, you see it?
You don't
Okay.
see it?
No, we see us. Yes.
Yeah, we
Everything
see
works.
we see us through that thing, and we see the screen. We see everything.
Final presentations.
Yeah. Oh, no. Someone
Already a critique. We're not even 30 seconds in. Sorry, Betty.
Which is what really matters.
I changed that just now.
Oh,
I never changed the date.
Oh, no.
Wait, is it 30?
Oh, yeah, it is the 30th.
But you ever get off? Yes.
Oh, the AC's gotta go off. We're sweating this out together.
We are.
Yeah.
Wonderful. Okay. Thank you. Oh, okay, wonderful. Is your mic on?
Yes.
Wonderful.
We are all good. Can everyone hear us?
Yes.
Okay, great. Thank you.
Perfect. So, hello, everyone. This is the last time I get to say it, but happy Friday. Bittersweet. So, welcome, everyone. We want to thank y'all for being here to see some of this research and how it's culminated over these really fast 10 weeks. So, just to begin, I'll be starting things off, and then we'll get to see everyone else's presentations too and their work. So, my project is some of you, so you can see.
Yeah. That's good. You're right there.
Okay, yeah, here I can ban away for you. But anyway, so my presentation, as many of you guys know, is going to be about my project Lie Detector. So we had a bit of changes along the way, but largely what I've been focusing on for this project is a specific type of signal called a P300. So a P300 is called such because it's this very specific sharp peak that occurs roughly 300 milliseconds after very specific stimulus. And this is actually a very rare kind of signal for EEG. You know, you don't really, it's uncommon in that it's so situationally dependent. And in particular, the P300 is really dependent on showing fast, novel stimuli, and is further heightened by really salient facts, things that people are much more aware of and personal to. So for example, you know, being shown pictures of animals, a P300 would only fire for pictures of your cat. It wouldn't fire as strongly for even pictures of cats that are similar to your own picture of a cat. That's how interesting the signal is, in my opinion. So what I really wanted to work on with this is seeing what we can harness in terms of the P300 signal with our materials and see if I could design a neural network that would be able to diagnose a true P300 signal from other neutral responses. So in terms of materials, the biggest materials I was using was the spike recorder, of course, because we're dealing with EEG. And then I also made a setup using the new Human Spiker Box Pro and a WIO terminal to send time signatures to be able to auto-record all my P300 data. So in terms of methodology, mine is a little unique because I really wanted to look at two different types of tasks when it comes to P300, a two-stimulus task and a three-stimulus task. The two-stimulus task is known as a traditional oddball setup, where one stimulus is simply shown less frequently and compared to the other ones. And I collected some of that, and it's a pretty simple test. It's really just to make sure that this base setup was working and could detect some sort of P300 compared to the stimulus. And the three-stimulus task is where it gets really interesting, because I took the same test group of people that had been engaged in two-stimulus tasks and misled them by saying that we were going to continue with more oddball tasks, but instead introduced them to a three-stimulus task, where along with a target stimulus that they were being asked to count, as is in an oddball paradigm, we also slipped in personal, highly salient images, either in a visual facial oddball test where there were pictures of unattributed persons along with pictures of themselves drawn from their own social media, or in a visual verbal oddball test where I showed them names of recognizable personas and also slipped their own full names into the mix. So in terms of the results, this is where what I'm really excited to talk about. So in terms of a base oddball exam, the two types of oddball exams that I did were a visual dot-based oddball exam with some very simple pictures of just colored dots that they were asked to discriminate between. You can actually see that there's a very high P300 signal comparatively, which is awesome, because this is a great baseline exam, really makes a good proof of concept for this type of visual P300. But I really wanted to expand beyond that and make sure that we could see this with other more advanced features before we moved into any sort of three-stimulus task. So what I did there was I used more complex images of, they were asked to discriminate a spoon from other pieces of similar appearing cutlery. And we can still see in the graph at the bottom left that you can see a much higher P300 signal, so more yellow compared to the neutral in that bottom left exam. And then moving on to the three-stimulus task with the visual facial and the visual verbal exams, what I really wanted to do there is compare and see what these two different types of signals would encourage as far as a high P300 response, and how they would differ between them. Because historically, most of this P300 data is done using verbal exams, but I really wanted to see how high visual information would affect this sort of exam. But what you can see actually comparatively, looking at the top, the right side and the bottom right side graphs, you can actually see that the probe for the visual facial exam, which is the top right, has much more yellow comparatively to the target and the neutral. But you don't really see that same thing for the visual verbal P300 exam, which I think is really interesting because that means that there's some sort of higher response going on with that recognition of one's own features, probably coupled with the surprise that I, went through their LinkedIn and stole some personal images. So those are the big types of data that I was collecting, and it was already really interesting to see that facial response. So moving on from that, I really wanted to attempt to make a model that could discriminate these features. So what I started off with first was attempting to do an amount of peak lining up, because sometimes the P300 signal can vary a bit within that 300 milliseconds, and then feed some of that filter data into a model between the probe, which has secreted information, to the neutral and the target when they're being actually asked to count. However, the unfortunate thing with some of the trials that I've done, even in some bootstrapping instances, is that it's really not that good at telling the difference between these smaller peaks. So what I attempted after this fact was just trying to see if it could discriminate at all between these sort of P300 peaks, whether they be the explicit probe or even some amount of recognition.
So what was the input to the model? Was it right at the plus or minus around 50 milliseconds? So basically these yellow bars. How much width of that bar? Is it from the entire screen that we're looking at, or is it just a segment of the center?
Yeah, so this entire screen, so this is about 0.3 seconds. So that was what I was feeding into the model.
That entire thing was synthetic.
Exactly, yeah. So those time signatures are what was being fed into the model. And what you can see is even still just being able to distinguish between neutral and non-neutral, it was having a very tough time doing so. which is unfortunate. So in terms of next steps for this sort of the project, I really want to lean into just hard coding my own model outside of this platform that we've been using called Edge Impulse to see if maybe doing some other alternate feature generation on my own could lead to any other different results. But in good news, that means there is a lot to be done in terms of recognizing these P300 exams. There's a lot of promise in terms of using these visual tests in a classroom, which I personally really like because I think these visual images make for a much more interesting exam on behalf of kids and their attention spans. You know, staring at words for a really long time can get very boring. But these sort of facial exams and object recognition tests can be very helpful in encouraging, long-term attention spans. Yeah, so that's the base of the project, and in terms of next steps, thank you so much for listening, y'all. I'm so excited to hear what everyone else is going to be talking about.
This is awesome. So, what I love about this, underneath your what is the P300, you're showing an average, and that's typically how it's shown in the literature, right? And then the other thing we were doing was kind of showing these pile plots, which we really couldn't get a lot of information on. We didn't know which line was which, right? But this is a different set of plot. I'm assuming this is the voltage across all the trials.
Yes, it's every session.
Every session, so that allows you to see the variability of the trials, which gives you an idea of what an AI, that's actual data going into the model. You can actually see right here. So if you're having a hard time picking out which one is which, if I just chose one of those lines at random, you probably as close as the AI is. So it's absolutely wonderful. And who drew those? You can hand drew those?
Yeah, I can draw these.
Wow. Wait, really?
Yeah.
Yeah. Yes.
Yeah, I got it.
Incredible.
Thank you. Appreciate it. Yeah, so that's the base design. Thank you.
Is there a question? Is there Q&A time?
Yes, in the results in general, comparing the P300 with the neutral, or in general the neutral with the target end probe, they seem to be a bit broader, so that the P300 is not only giving maybe a stronger peak, but also a broader kind of signal in general. Is that true, or is it just an impression from the graphs?
No, no, you're absolutely right. Generally speaking, the probe or the P300 does give a larger, broader peak comparatively to any sort of peak that's going to be seen in the standard response. So what I also really want to do is attempt some sort of either wavelet transforms or even some sort of early averaging recognition, because anything that would really slow down the amount of time or condense the amount of time needed for these exams is absolutely helpful.
So is the one you're showing here under the 1 to 300, is that your data as well?
This left one?
Yeah.
Yes.
Is that the same data from here?
So this is an example of a sample auditory P300.
Okay.
That was also sampled using this exact same setup.
But I feel like, let's say that even in some of those trials, and the results were like this one here, you said that it was pretty accurate. Was this a representation of what you saw normally?
Yes.
So it seems to me that the biggest change is the temporal shift, a time by 100 milliseconds. And you may have gotten rid of that by centering around the peak. So you've taken away the most distinct thing between the green line and the red line by taking the green and red peaks and aligning them to each other.
Very good point.
Thank you.
And I think that I can see that the green line is higher, which is why you get that higher peak there. But I think if you left it centered around the image onset and maybe just look between, that time period, you might be able to see a separation of the P300 signal away from them.
No, so I certainly agree. I think, this initial task was throwing the baby out with the bathwater, so to speak. I agree. I think that's also a great next step for this, to see if there's any further discrimination that can be applied. But previously, I have thrown this into a model without any sort of peak manipulation, hoping that those temporal shifts would be enough to tone out the difference, but it still hasn't.
I'd like to see that the laser plot, for lack of a better word, with this alignment on zero, to see if that would be able to be separate.
Absolutely. Thank you.
Wonderful.
I have questions.
One question.
No questions?
Yeah, there was something.
I said, how does this, your thing, Like, how does this compare to previous lie detection stuff? I know you said to move that away, but I think.
No, I think it's great. So the thing that I personally really like about P300 and its potential for the world of deception detection is that it doesn't rely on stress testing. Because historically, I'm sure many of you are familiar with the polygraph, it relies on looking at your autonomic stress responses. But the unfortunate thing with that is that those autonomic stress responses can be correlated with a lot of other things. For example, I brought up if you go to a CrossFit class even before you undergo a polygraph test, that can contaminate the results because it's, you're just going to be more sweatier than you are on average, or even if you're just more anxious, those things can make false positives really common with a polygraph. But the great thing about the P300 and its use in some mock crime scenarios and some research projects is that it really doesn't present false positives at nearly as high a rate comparatively. And also, because it doesn't involve that stress testing, you don't have as many corollary factors that can be involved. Of course, like as is with any sort of lie detection, there are countermeasures you can employ, but it is much more difficult to do this in a P300 setting compared to a polygraph. Where the goal of the polygraph is just staying as chill as possible the entire way.
Very
Great.
cool.
Yeah, no, I think this is good.
Pretty awesome.
Huh?
Pretty awesome.
Sarah's casting.
Fantastic. So I'll just... Oh, no. Wow.
Can you refresh your
Absolutely. Oh, got a live update?
Well,
Fancy.
not really. Wait, I'm gonna try to do this also from Sarah. I told her she should just present all our projects at a conference. Just slide one by one. Like, they're here, she'll just figure it out.
Yep.
Oh, yeah. I'll bullshit for you, yeah.
Yeah, exactly. And here we have something to fill out. What's in the meeting today? I'm curious. Who all made it?
You want to switch seats and sit
Chris,
the camera?
Yes,
Where's the
sir.
camera right now? What's up there?
Okay, cool. Hello, everybody. So, as you know, the past 10 weeks I've been working on a project called FOMO glasses. I want to ask the audience, how long do you guys think you spend blinking? If you didn't, no, you didn't know. How many times?
A few.
Your whole life?
A little
I
while.
regret to inform you that you spend 3 to 4 years of your life with your eyes closed due to blinking. So, aren't you worried about what you'll miss? Well,
Just
worry no more.
I wish we had a solution.
And that's only if you live to 80 years. If you live to more, that's more years. So, worry no more. FOMO glasses are here to help to show you everything you're missing. So, my project uses EOG signals and machine learning to create a pair of glasses that take a photo every time you blink, so you miss nothing of your life. Now I want to ask, well, first I'll say, like all these projects, our body generates electricity, and that's what all these projects are measuring this electricity and manipulating it, and making cool things out of it. And for my project specifically, we're focusing on the eye. So a lot of the charges in your body either have positive charge or negative charge, and your eye is actually unique because you have both. The front of your eye is positive and the back of your eye is negative. So this creates a very unique signal when your eye moves around, because signals either go up and down or left and right depending on what direction you're looking. And this makes my project, it made my signal part kind of fun compared to everyone else because it was a really strong signal. As you can see here, I have these lovely graphics from the textbook of my own EOG, I will say. And you can see as you move left and right versus up and down, there's a clear distinction, which is why, as I've said, I chose to use 2 sets of electrodes to really find a pattern that my AI can find. The struggle with mine is how do you differentiate that from other eye movements? Because your eye is always moving and it's very sharp movements, strong, and how do I get that unique signal out of all the other noise? Well, I applied some filtering, as you see in these little graphics, to squish. I use the word squish, that's okay. To squish all these low frequency signals down so these really sharp, unique shapes come out, and once we trigger on that filtered data, we could send this raw data to my AI model that's hopefully on a pair of glasses. As you can see here, it's a really simple model. It's only 8 neurons, 16 and 8. I'd actually just be updated. It's only 8 now because otherwise it overfits because again, this is such a nice signal. And here you can see the average shape. They're all very consistent. Send it to the model. It classifies. Deploy that onto an Arduino and wear them. And that's pretty much summary. You can find them at your local backyard brain shop. Pick them up, and then I'll throw this closer away. I have my money.
You should talk more about so what was before and after high pass filter? What does that mean?
Well, before and after, so a high pass filter means that anything that's a high frequency will make it through the filter, while everything that's kind of a longer, more drawn out movement, like looking left or right or up or down, will get squished so that it will not trigger our AI model to classify, because we know that's not the signal we're looking for. We're looking for that really distinct, and now this doesn't always work, so there's obviously still eye movements that are sharp enough that make it through the threshold, and if we just classified on that, our accuracy wouldn't be horrible, but it's not as good. It comes out to about 80%, maybe 79%, but once you trigger less, your AI model has time to classify on the really strong signals, and then you get that really good result.
So you said that moving your eye could lead to those like low frequency wave changes, but when you that top graph on the data collection, what is a saccade exactly?
So if you can see, it's kind of hard to see on the screen, but these two green lines are those two blinks, and I chose that image because it shows just how much variance there is even with the blinks. The first one is very light and fluttery, the second one stronger. But even though they're so different, there's a very distinct downward shape that you can see versus everything else is those saccades. The most important thing in this reverse oscillation of positive and negative is that in saccades, usually the signals are moving away from each other, and they keep crossing each other like this. The blinks are one of those unique cases where, depending on whether you have the positive here or here, this image actually has a reverse, so I should switch that. But they kind of jump together, and even if they go apart in a very unison and quick way that no other saccade that I've seen does. So, but if you see those, they're kind of random, like that one jumps up. And I'm also only triggering on the first signal, I should clarify that, because that is the most distinct. Which is
And so, what are you feeding into the model? What is this data right here, all blinks?
Yes.
It's just, there's no pre-processing, you're just sticking in the raw data after,
Yes. Yes. I trigger on the filter data, but then I go back and find the corresponding window in the raw data, because it's more data rich and detailed, because I have to find those patterns. Yeah. You can also include a number of fast time filter data. I do have that. And this hardware is what Max is working on. I was going to label it, and then I realized I didn't know what the parts were, so I have to meet with him. So he can tell me. I was like, I'll draw some nice lines. Yeah, and then hopefully we'll have some nicer photos. I kind of like that one, but nicer photos for the outcome.
That was
kind of
cool,
words that I also, I was also going to ask if it's okay if I talk about implications of the project, or is that like
Oh, you can put this in your project. Yeah. What does it mean? What's it all mean?
yeah, like I can go like a little bit of philosophical, like what we missed, and also just like
I think
issues
that's
and mobility.
Cool.
It's very good.
I think we should do the thing that you did with your poster.
The video,
Yeah,
intro video, like 2 to 3 minutes.
yeah, I think it's great.
That's amazing.
Capture it on YouTube. All right.
And then ideally you have the glasses in and you can take a photo because that's what they really care about.
Mm-hmm.
Let me wear it. Okay, that's all.
Awesome.
That's wonderful.
You did it.
You did it.
We'll go sleep, guys. Good luck.
All right, bye.
Ari, quick question.
Yes.
So it says here that you're using a convolutional network, but the data is kind of time series.
Yeah, that was the default. I made this like neural net processor visualizer. I have to take the convolution out.
Oh, okay. Just checking.
Yeah.
So the one at deployment is closer.
Yeah, it's just two dense layers.
Excellent.
2 dense layers. Okay. Cool.
Yeah. Yeah, we can take that second one out. Sure.
Good eye.
Good.
Nice.
Oh, it's me. Mm-hmm. Whoops. Come back. Okay, good morning, everybody. Last slide. What a shame. But it's a good one. So, my project was a little bit different than those of my peers. Mine was less artificial intelligence and more fish intelligence, which is fine. So, we were hoping to answer the question, do fish play? Now, where do we begin? So when we think of play, we know that people play at all ages. We know that monkeys play, cats play, dogs play, horses play, goats play, dolphins play. But where did that come from? How did this function that's shared all across the animal kingdom come to be? Has it been with us from like 500 some million years ago when our brains were the size of a pea, or did it evolve as our brains were evolving to become more advanced? If you look around for scientific literature about where play came from, particularly fish play, fish intelligence, fish cognition, fish behavior for the sake of talking about fish behavior, there's not a lot except for one random unofficial publication from the 70s and one that's a bit more recent from Dr. Gordon Burkhart at the University of Tennessee, who found that 3 African cichlid fish were playing with a thermometer, or at least interacting with it very uniquely. So each of these 3 fish would repeatedly knock around their thermometers in a way that resembled play. And not only that, but each fish would interact with it in unique ways. So one of them would go really crazy and knock it from one side to the other. One of them would make it wobble by knocking around the top, and one of them would mostly attack the bottom. So do fish have their own personalities? That's a question for another time. But all that was left to do was qualify this as play scientifically. So Dr. Burkhart has proposed 5 criteria for defining play behavior, and you can read along with me on the top left. The first is that it can't serve an immediate function, so it has to be done for its own sake. It has to be voluntary, so not like trained or taught. It can resemble a functional behavior, so like play fighting in puppies can look a lot like real fighting, but it's different in context, in facial expression, and the sounds that they make. So it looks a lot like fighting, but it isn't actually fighting. It has to be repeated, but not pathological. So it has to maintain an element of spontaneity, and the fish has to be happy, or at least not stressed when it's happening. So not hungry, not sick, not under threat in any way, because in those circumstances, their behavior will change, but not because they're having fun. In fact, just because of the opposite. So we took this information that these fish, these African cichlids, were playing with their thermometer in their aquariums, and we got some of our own. And we stuck them in a tank and gave them some thermometers, and we watched. Our fish, for some reason, didn't love the thermometers. They don't appear to be playing with them in any way. But one compelling discovery is that one of our cichlids really liked to chase around a laser pointer and try to catch it and run after it, which was very interesting and exciting. And not only that, but he showed preferences for different colors. So he preferred red over blue and green, and blue over green. So in one of my adventures to the pet store, I took along my laser pointers and I went to the fish section, and I shined my laser pointers into each aquarium, and I found that over 80% of fish species that I looked at were interested in some way in chasing around these laser pointers. And just like our cichlid, they also preferred their own colors. So we can see that 34 of about 60 fish preferred only red, just like our cichlid. And then 6 of them preferred blue, 6 of them preferred all 3 colors, 10 preferred red and green, 2 preferred only green, 5 preferred red and blue, and only 1 preferred blue only. So that's very exciting. And Sarah, there's actually, you can click on that little button on the big computer, and it will play a video, and you can make it full screen. It shouldn't have sound. Okay, perfect. You can't really see. But one additional exciting discovery is that you can sort of see this goldfish up there. He's not doing much. And then after about a minute, towards the end, he joins everyone in chasing the laser. So we'll see that in a second. So cool. I know. It's very blurry. I tried to up the quality, but it wouldn't let me. There he goes. Yep. Yeah, so see, he's trying to catch up with everybody else. He has FOMO. Yeah, so that was a really exciting discovery. And you can see, if we're able to get back to it. Oh no, disaster. Can you just escape? Yeah. Okay, perfect. So you can see all the way to the left, that little sticky note thingy has a breakdown of all of the species who showed varied levels of interest. So we can see at the very top, goldfish showed no interest when it was just a tank of goldfish. But that guy on the bottom joined in with everybody else after a certain period of time. So that's very exciting stuff. And we think that we're probably one of the very few people in the world who know this information about fish. So that's a lot of qualifiable stuff, but how do we turn it into cold, hard facts? Well, we make ethograms. So in the middle, we can see ethograms belonging to our cichlid fish. On the left-hand side is an ethogram of him. I thought that was the air conditioner. An ethogram of him, just normal, everyday, not stimulated, just doing his own thing. And on the right is an ethogram upon and during presentation of the red laser stimulus. So they're a little bit busy, but they're easy enough to read once you know how. So the sizes of the circles correspond to time spent actively performing each behavior. And the thicknesses of the arrows correspond to how likely the fish is to transition from one behavior to another. So there are quite a few differences here, particularly there's not as much variance in the behaviors being performed at each time. And also, the quick swim behavior is the one that's performed during the least amount of time in just normal everyday, but the most amount of time when he's playing with the laser. So that's very exciting stuff. And we can't quite yet answer the question of whether or not this is play. I think we'll probably need to do some more tests, have some people go to pet stores and get more information about fish laser tag. But until then, it's a solid perhaps, and exciting discoveries were made along the way. And that is all. Science, baby.
So your fish, the cichlids, ended up ignoring the laser after time.
No. So that was kind of a confusing bit. So Tim had been, I'm not sure how much he was exposing these fish to these lasers, but after a while, like last week or something, he said, hey, they're not playing with it anymore. And then I tried and they didn't play. And then I tried again like the next day and they were into it again. So I wonder if they just become less interested. They haven't completely lost interest.
If you look at those 5 criteria, does that disqualify the play at all?
No, not these. The one thing that might, I couldn't squeeze it in here, and I think Etienne, you had mentioned this, it might be related to eating behavior. But the reason that I don't know if I'm entirely convinced by that is because, you know that plant that sits at the top of the middle fish's little space? When I would drag that around, he would chase after it. He wouldn't try to eat it. He would just chase after it. So that's probably, it probably has to do with something that we don't yet know. It could be just a reflex that if they see something moving, they go after it, and their tiny brains can't process that it's not worth going after it.
I think if they have a certain size, they're definitely huge.
Yeah,
Just
like the laser dot.
Yeah.
But the big plant
But the big plant, yeah.
is something entirely else, and it's a similar chasing behavior. Yeah. So we can sort of define it as play, but I'm sure that a lot of real science people would be like, girl, please.
Yeah, so and the one I'm stuck on is 3. Differs from functional behavior, appearance, and stuff.
Mhm.
And do we know? And then like,
I could probably phrase that better. But
well, no, but I mean, I think I get what you're saying.
Okay.
So the question is, do fish, do cichlids chase after small water bugs
Exactly.
on the floor? I don't know if we know
The thing
that.
is, you let
I
them-
think I would have to do a real field test and just go to Africa and see, probably, is the next step.
You let them have it though sometimes, right?
Mhm.
And do they like fight it?
But then they would keep going and keep chasing it.
Like it's like, yeah, I wonder.
Yeah.
Because these fish have also probably never chased across the entire life. These are their instincts.
Right. Yeah.
So out of those 5 criteria, which one do you think is the most testable?
The most testable, I think probably incompletely functional. Because I think that sort of sets you up for everything else. Because if it's not pathologically stereotyped and not trained,
What could we control? Is there something, an experiment that can be done that changes one of these parameters that allows us to determine if it's
What if you made 2 that were like every time they chase like one color pointer, they got like Do they keep it every time they chase another one, nothing happens, but they stop chasing that one? Or they keep it? Is that kind of
Yeah,
hard
well,
to do? It's just an
With
instinct.
fish, it's difficult
What
because
would that address? Which one would you fire?
It would be the function of it. Like,
Yeah.
could they not, maybe it would somehow make them think, okay, this chasing whatever this is.
I don't know how
If it
doable
doesn't
that is
work-
though, because if you feed a fish too much, it dies.
Yeah.
So you would have to.
Well, what about a reward-based feeding trap? Because like it's shown in other
Mhm.
animals that you play that they prefer reward-based feeding
It's been
traps
shown in
instead of
fish,
just
too.
eating normal. Oh, really?
Yeah, I showed a video on one of my slides. This lab is doing experiments on cichlids where they have to, you know, those colorblind tests where it's like a bunch of swatches of color and then there's like a number in the middle. So it's kind of like that, except there's just one dot of a color, and they touch it with their nose. The different color, they touch it with their nose, and then they get food. And they know how to do that. They do it every time. So they've been trained to do that. That's not a playful behavior. That's training. That's just reward based.
But
You could
what
juxtapose
reward-based feeding, what they do is you allow them a choice between the ability to, you know, be fed whenever normally, or to have that sort of thing where they actually have to engage in something that's, you know, voluntary for them.
I'm not sure if I don't know
I
how to
don't
do
know.
that.
I don't
don't
know
eat
either.
fish.
What about that last one?
Mhm.
So what could we control in that last one? See if it's played.
I mean, one thing could be the types of fish who are together in one place. So, like, when our fish are cichlids, they're aggressive. So they already know that they're under threat. And this middle guy would still chase the plant around when they were all together. So that,
Is there, what is stressful to a fish? And could we recreate that and see if they chase it when they're less, when they're
Mhm.
stressed versus when they're not stressed? But that would, if it dips, if the behavior dips when
yeah.
something is threatening, and if there's a predator about to eat you,
Mhm.
you're probably not going to take this thing unless
You still want to
you
do
still think it's food. And so that's something that we can actually measure.
Yeah.
We have to do some research and find out. I'm sure that people
find
look
a
at
fish that they might.
stress responses and
But for that, I feel like you would have to take the predatory fish away during times,
Yeah.
non-trial times, and then put it in during real trial times. But that might be unhealthy for the fish, putting them back and forth like that. So I wonder if we could do something just to replicate and then take it away.
There was
Yeah.
an experiment that you're showing that had that they were very careful about who was next door, right? So I think
Mhm.
that is getting to the fifth
Yep.
here.
Yeah. Yeah.
Having the fish right next to them.
Yeah.
May just be enough. I don't know. There's,
Just do black
but even
dividers.
if, I don't think it's the fish out. I mean, just the dividers.
Yeah.
Like a black one versus a blue one.
Yeah.
Yeah. Or we could do,
Like,
Just
you could put like just a door in the thing,
Yeah,
and then like
yeah.
open it sometimes, and then shoo them back in when it's not.
I think if we wanted to publish this, I mean, that'd be a cool. That would be an experience, not just behavioral observation. You actually
Yeah, an
have
actual experimental test.
some
Yeah.
data that's based upon this criterion that shows that. And I suspect that if it was truly stressed, it wouldn't be able to
Mhm. Yeah.
I think the fact that they get bored also includes that.
Mhm.
It's novelty. That, I don't think they care about novelty when they're about to eat. So,
Yeah.
that's it.
Again,
One question, Sophia?
Yes.
Yeah, so this is great. As a former fish researcher, I have to say there is research on fish tracking small visual targets, including laser pointers. If you Google on YouTube or it would be great to see how your findings kind of relate to. I can post one. Oh shit! Here we go. Here's one paper that does laser pointers, but there's a lot of research on how small visual targets are processed in detectum and how detectum kind of converts that into a motor, a directed motor response that fish use for prey tracking, so kind of for eating.
Mm-hmm.
But usually it's restrained fish or people vary the size of the target or something like that.
Cool. Yeah, I mean, it looks similar.
Yeah.
And that's a laser. That's an actual photo.
So this says here, they tested some fish and observed behaviors: biting, chasing, hiding, posing, lunging, and retreating. Lunging behavior increased significantly for both species tested upon exposure to laser pointers, and none of the other behaviors changed significantly. So it's similar. Maybe I wonder if lunging and the quickly swimming is, yeah.
Something like
Posing, I'm not sure what posing is. I'm not sure.
they're like still in the water.
Yeah, I don't know.
I don't know.
Right. Cool.
Navigation is fun. Everyone loves the fish.
Fish are fun. The fish are fun. They're the most easily marketed.
I see the next person, right?
Yes.
Good job.
Oh, it's playing my video. It's playing my video.
Oh,
Oh, that one too. Tried to tearjerker.
oh.
Alright. Morning to everyone and all.
Good morning,
I am here today to talk about what I've been doing over the past 10 weeks. So maybe you have an exam tomorrow that you are studying for. Maybe you have, maybe you're taking the final kick of a penalty shootout in the World Cup final, or maybe you have a gambling addiction and you have you put your entire life savings on the line on the poker table. Or maybe you have a final presentation to give for your 10-week summer college.
That's the most stressful one of all.
The latter is the most stressful, right? And I'd rather do some testing on those types of stress signals. But alas, I stuck with the gambling addiction. And I'm now, over the past summer, I've been working with poker games and poker players and determining some patterns between players who play poker and certain things that happen on the board. But in general, stress responses are a very universal part of the human experience, and that's something I was really interested in from the get-go. And so poker was kind of an avenue for me to look into that stress response and see how are we really better than a computer? Are we more capable of controlling our internal physiology than we think or that we're capable of? So poker was that avenue for that, as I mentioned, and I looked at two signals during the course of players playing poker. The galvanic skin response was one very key factor to my data collection, and then also the pulse, your heart rate, was another key factor. And running difference, I'll get to that in a second. But the pulse and the skin galvanic response were the two key factors that I was collecting as players were playing poker. And I was trying to see, is there a pattern between these two data streams and whenever a player decides to voluntarily bluff that we can detect? And so that's what I kind of focused on in the first couple weeks. I tried to see if there is a signal in general that we can detect. It was kind of an on and off, and I wasn't really confident that there was a certain signal that I could reproducibly create every time a player decides to bluff. And there are a couple of reasons for that, which I'll explain a little bit later on. But I was able to find a little bit later on through some data visualization methods, and thanks to Alexi and some of his help, I was able to visualize the data in a different way. And so that's what you see in the middle part of the analysis poster. So I've shown here in the top row of the middle column are the same full session of poker with the GSR response on the left and then the pulse on the right. And so you can see in the GSR and the pulse, every point that the player made a conscious decision to bluff, I have highlighted the next 15 seconds after that with those red windows. And in the GSR graph specifically, I did some analysis, and one of the analysis features that I created was the running difference plot, which are all those red spikes, and that's what RD stands for. The running difference plot is essentially an absolute value approximation of the first derivative of the skin galvanic response. So essentially the slope. How fast is the slope changing? And what you find, which is really cool, is that slope is in fact a very important feature of determining bluffs within the skin galvanic response. So that's what you see in that middle left graph with the bluff window zoomed in. So you can see in that 15-second window, there's a general spike in the running difference plot, which is characteristic of that sharp down decrease in the GSR response. And the reason that's so significant is if you compare that to the graph below it, in a neutral window where there was no bluff occurring and the card was just flipped over, and either the player did not hit a hand or nothing eventful happened, no such change in the running difference plot. And so that was one thing I saw very characteristic about the GSR a couple weeks ago, which I was happy to see. And then in the pulse, we can look at it in a similar fashion, except instead of just an analysis on the running difference, I instead looked at the difference between the end and the beginning of the 15-second sample to determine this overall average slope. So if it was positive, it was characteristic of a bluff, or if it was negative or decreasing, it was characteristic of a neutral window. Now I have to say, this pattern that I noticed is not characteristic of all bluffs and all neutral time periods. And that's for a couple of reasons. One of which is, in general, this idea of a player bluffing is subjective to them as well as subjective to what happens inside them. So each bluff signal is not created the same. No two bluffs are the same. Some are less stressful and some are more stressful. And so that was creating a little bit of a confusion in terms of my data analysis, because as you'll see in, what I'll talk about in the future directions, sometimes, actually most of the time, anytime a player went all in, regardless of they were bluffing or not, it was characterized as a bluff because the stress response was just so high, it was similar to the pattern that would show up as a bluff. So there were a couple of problems I'm running into in that fashion. But in general, the trend was upholding pretty well, and I was pretty happy about that. And so I decided to, I worked with the machine learning model a little bit, like in Edge and Pulse, just plugging in all this raw data, process data. It wasn't turning out the way I was hoping to, so I just decided I want to see actually just how well I can classify this with Python. So that's what you see on the top right. I did a Python hard code classification system that used both the GSR response with the running difference plot in conjunction with the pulse to see if you could classify bluffs versus no bluffs pretty effectively. And you can see the sample sizes of each of the bluff and neutral in that box. But in general, the bluff was able to be classified correctly 60% of the time. And if there's a neutral window, about 77% of the time. And a big part of that, I hope to have a higher classification for the neutral signal, but a big part of the reason why it was 77%, as I mentioned, was because sometimes the neutral signals will be classifying as bluffs due to all-ins and other like stressful, mini-stressful periods along the book around. But that's where my project ended up being over the last week, and I think that was a pretty significant development, something I didn't see coming, really, because I was beginning to question, the whole idea of whether a bluff could or could not be detected with the methods that I was using. But now the next step is to use that in a machine learning model, which is the whole general idea of the summer and also what I was aiming for at the very beginning of the summer. And so I just plugged that in. I plugged the I plugged the running difference plot from the GSR and the pulse into the machine learning model, and that's that image you see right there. So classification, kind of random in some ways. There's a kind of cluster of no bluffs on the left, and everything on the right, kind of 50-50. So there's a lot of work to be done in terms of the machine learning aspect of my project, but that is definitely a future direction I'm looking into. And either way, though, I think it's pretty cool that there might actually be a signal that I'm working with. It's pretty inspiring. So over the next couple of weeks at home, throughout the school year, I'm just going to play around with this and see if there's a way we can get this to work through the computer as well.
Through AI.
Through AI. Yeah.
You've been working with this all summer. You've been doing the broker thing, working with these signals. Do you have any sense for any other situations that like some similar analysis might be useful, maybe even better than broker?
Oh, like that. A couple of cool things. I mean, I can share some patterns that I noticed. So one of them was, surprisingly enough, when people laugh, there's a very, very clear difference in the skin galvanic response. And I think Sarah and I were playing around with this in like the middle of the summer. But when a person laughs, it like immediately drops. Like very like faster than a bluff or anything like that. It would just like completely drop, which is really interesting. So maybe if there's a way, yeah, it's like I don't know if that's related to happiness in any way, if that's just a shaking of the body when you laugh. But if it is related to happiness or some type of endorphin release, I think that would be kind of cool to maybe detect.
You said in the pulse or the GSR?
In the GSR, yeah. Maybe there's a way to determine a computer model can determine what you like when you see a bunch of images and like I don't know, maybe it can determine your favorite ice cream flavor or something like that.
Speed out your spouse is cheating.
Or a little bit more serious. Yeah.
Just a technical. So in the results, you say Python hand code classification. I think even edge impulse is Python to generate that one.
Oh.
So I think we should be a little bit. Just maybe we can ask Alexi what we can look at that code. What is the how is it? I mean, what is
I wrote that code actually.
All right. Well, so it could be written in any language, right? So the language doesn't describe the classifier. Sure. We should probably just put what type of what discriminator was it?
Sure, that's a good point.
The linear discriminator.
So what I was actually doing is, as I mentioned, I combined the two analysis from both signals. So for the running difference plot, I found the average of the first 2 to 3 seconds, actually 3 seconds from what I remember, of the first 3 seconds after the bluff window and the next 12 seconds, and then found the peak between both of those, so the peak at the beginning and the peak in the second window, and compared that difference of the maxes. And if that max was above a certain threshold, then I would classify that as a bluff. And then in conjunction with that, I used the pulse to determine what the slope was, like whether it was a positive, negative, or decreasing slope. And if the pulse was, in some cases, as you can see in that top graph, if the pulse spiked really high, that actually correlated with bluffs once in a while. So combining those two factors together, those two kind of thresholds together, is what I use to classify.
Yeah, that would be a linear discriminator.
Okay. Yeah, linear discriminator.
I have a question.
Yes.
So these red windows are 15 seconds after the person actually did bluff in the game, right?
So that window actually is not after the bluff. It's somewhere within that 15-second window is where we hope to see the bluff signal, because exactly the dashed line is where the card was flipped over.
What does that mean that the card was flipped over? I don't know how to play poker.
Okay, so in poker, if you look at there, in that image, how poker works basically is that you're betting throughout a round, okay, and then within that round, there are 3 instances where cards are flipped over. So the first time is when the first 3 cards on the table are flipped over, and then the players will see that and react accordingly based off betting more.
Basically the second the card flipped over, they'll know whether or not their hand's going to be good or not.
Yeah.
They're trying to think about
So we're testing, we're testing their like initial reaction to seeing what the cards are, because and that's why I've only been taking players who know poker really well, because they kind of internalize whether or not the cards help them or worsen their situation. And then the second those cards are flipped over, if a player chooses to bluff, they would have to decide within that 15-second window, because otherwise the game would just move on to the next card.
Okay. Yeah, I know like 10 people have explained poker to me. It leaves my mind every single time. So do you have them, is there a way, would it be helpful to like have a button you press when you decide to bluff? Like you make the active choice?
So that's a good point. It does kind of involve the player itself to be helping with the data collection. So I don't know if that's going to affect the data in any way. It's something that I was doing initially actually too, because when I was collecting data on myself, I had to click the event markers but also play the game, and I feel like that was affecting the saliency of the response that I was seeing during the round. We could do that, but I think the better way to classify, because that wouldn't really help with live classification, because the player isn't going to be clicking a button during a real game saying, hey, I'm bluffing now, because then the whole point of the model is to guess when it's bluffing.
Yeah.
So I think the better way probably would just be to, whenever the cards are flipped over, that's when the model would start classifying. And then if it classifies it as a bluff, maybe the player's bluffing. If not, maybe not.
Yeah.
That makes sense.
Yeah.
I think you should put the word running difference in there somewhere.
Yeah, we did not do that.
It's underneath. The running difference plot containing red spikes indicates.
Yeah.
It's under the full poker session GSI.
Yeah.
Maybe bold it or something. So
Yeah.
Or put RD in parentheses.
Yes.
Yeah.
Nice. Good job, Sachin.
Do you think you're gonna get it with more data?
Yeah, I hope so. That's the only really plan of attack I have right now. Increase my data sample size.
And a better poker player. So that really helps.
Maybe, yeah. That'd be good.
Maybe-
I mean, ET's
but
pretty
also-
good. He got me a lot of money. So.
It's like good players, but not too good that they control their.
But I
Yeah.
mean, the previous research, like the reference that I was.
I'm sure that didn't matter,
It
right?
should have didn't matter.
Yeah,
I remember that.
Regardless
Yeah,
of whether it's a beginner or not.
yeah.
Did they mention? I was wondering, did the paper mention any sort of use of countermeasures, like physiological, personal countermeasures?
What do you mean by that?
Like drugs.
Well, it's drugs, but like in other sort of like autonomic system testing, you want to look for ways that people try to avoid having their stress be detected. So sometimes it's like people reflexively thinking of something when the stimulus is presented to make them, more chill in the sense that they're trying to not have their life.
Like they go to a beach in their
That would be
mind.
something.
That's cool. That's
It's
interesting.
actually an interrogation tester that these people.
I think the paper didn't talk about that specifically, but I think one thing that they did that I did not do in order to prevent that from happening was that they used real money. So a lot of the times, like the players would not want to kind of like their full focus was on the game itself and producing results that were beneficial to them.
What I'm hearing is you're going to start a poker club at King's.
Okay, so I mean, there already is. I just
Oh,
gotta
yeah, you got to go
Gotta
and
join
like,
the
okay.
house.
This would be the neuroscience poker club.
yeah.
Good for science.
For science, absolutely. Wonderful.
Great. Good job.
Nice.
Yes.
Freddie with a QR code. Oh, never mind.
No.
Alas.
That's
I'm so excited.
that's for the printed poster.
Sorry. Oh, okay.
But yeah, so let's talk robots. No, just kidding. So the overall goal of this project is to control a robot hand using surface electromyography, or EMG, which if you're not familiar with that signal, is just a signal that appears whenever you move your muscles, performs a specific gesture. So for this project in particular, we're trying to capture EMG signals from 5 different muscles in hope that we can mimic the flexing motions of individual fingers in a robotic hand. So in order to do this, we take a couple of trials. In each trial, the subject will just perform or give samples of each individual gesture. And at the very beginning, we'll also include a maximum voluntary contraction task that will allow us to normalize the rest of the data set and use data across sessions. Now, once we have collected this data, if you look at the averages for each individual gesture, you will see the signal features indicated in the second block. And the idea here is that we can observe very distinct peaks at very distinct channels. And we have unique energy signatures at each individual channel. So for instance, if you look at the pinky versus the ring, you would see that the blue channel is higher, whereas in the ring is the green channel is higher. So if we do a Wizard of Oz test, we can see that these profiles are unique enough that maybe if we're able to see the difference, we can hope that the machine learning algorithm could pick up the differences as well. And sure enough, it does. When we look at the output of the classifier, at the input of the classifier to our feature embedding space, we see we have pretty distinct clusters. I mean, it's not perfect. Ideally, all these clusters will be separate. They'll have more distance between each other, but we still see, they're really is pretty distinct. So when we train our model, we achieve around 87% accuracy on training data, and then when we present it with data it has never seen before, we achieve an accuracy of around 73%, which is, for our particular task, I think it's acceptable, right? Missing 3 out of 10 gestures, it's not that bad. So once we have trained our neural network, we deploy it to our AI-enabled microcontroller, which is in this case an Arduino, and we try to do these classifications in real time. We collect data using a multi-channel EMG amplifier from all 5 channels. We feed it to the neural network, and then we use the output of the classifier to move one motor at a time, depending on which finger was the most likely to be correlated with the data we just received. So just as a way to show you how it looks like, I'll just have a demo played out here. So can you click on that video, please? Yeah.
So cool if you have a video. That's it, man.
What? Look at it go!
There's a clap right there.
Wow, bravo!
Dancing Kinky. Yeah, that last one.
That's my
So great.
All right, so 3 things I have to address from this video. Number
What's
one
funny
is
is that it looks like inking would be the easiest.
it is in fact the easiest. So that's one of the things I wanted to address. You can see that when I move my pinky, the hard hand starts jittering, right? Which means it's actually responding to the classifying. It's just some hardware issue that prevents it from actually closing.
Yeah, there's something in the water, right?
Yeah, I think there's some friction that I have to overcome, but that's more a mechanical design thing than actual software stuff. Second thing is you can see that the latency is not bad at all, considering that I'm taking about 0.25 seconds of data to react whenever a activity has happened. You can see it's pretty fluid. Like it almost follows exactly the motion of the finger when it classifies. So that was very important to me. It makes me think that we could use more neurons, better
It
models.
seems like when you move the pinky, it wants to know.
Yeah, now
That's what I'm saying. Yeah,
And then it goes,
What is that? What is that?
It's literally the hardware, like the motor.
Yeah.
There's something
Finger,
like don't let it. That's
So it would have done.
classification. It would have done it if it was fixed and done. Yeah. You
Yes.
can't get whoever made it. Yeah, no.
And then the thumb was also going where it broke, right?
Yeah, I
Yeah.
just didn't. I just chose not to show the thumb because of that particular video was broken. But
Yeah.
yeah, that's a good point.
Mhm.
How does want to classify? I think seems to be the middle finger and the index finger.
And then do we have an idea of like how often? So this is the training and test accuracy.
Yes.
But do we have an idea of how often when you move your thumb, does the thumb move?
We do not. Unfortunately, we ran out of time, but that's definitely something I wanted to try. Confirm that that accuracy right there sort of translates over when we do it in real hardware. That would be like an easy thing. Just have a person do the thing. Anytime take some statistical analysis of that and see how that performs.
It might be useful to have accuracy of each finger up there.
That would be too.
You just directly see the shape corresponding to your act, which is really fun to make sense. It makes sense that index and middle are being classified less. And I assume pinky is being classified well.
Yeah. Another thing I want to add is just I used 3 sessions for this training, which is about 150 samples for each finger in order to attain this sort of classification. I was considering adding more data, thinking that perhaps it will increase the accuracy, right? Has more data, which is mean a better model, but I started to see some marginal returns. So the first time I did it with just one data set, I achieved around 68% accuracy. When I added when I added the next data set, I jumped up to about 70% and then only to 72%. So it seems like we're reaching that marginal return curve. So if we were to expand this or try to do it differently, we should definitely start looking at maybe different models that could capture the features of the signal in a better way, or perhaps even look at different neural network architectures, because mine is just classic feed-forward, which is just as a default to see if this works. But no, overall, I'm pretty happy with what I got here. It's definitely a challenge to translate everything we did in the signal processing domain, data analysis into real-time Python code.
So do you think even with 10,000 flexes for every digit, you would not succeed the 75%?
I would say you might be able to do it, but I think that's brute forcing, right? I feel there might be a better way to do this. And, I haven't reached the edge impulse limit, but apparently there's a limit to, how long you can train. So, at some point, you can not just keep adding it, right? So, yeah.
But let's just say the maximum. You think that this is like already the plateau? From that setup.
I think I'm gonna add 2 more data sets just because for the sake of completion. Everything seems to be 5, so 5 sessions.
I really like this results of it. I would suggest just one more plot. For example, when I feel like you're kind of mixing in the results and the methods throughout each figure. It might be interesting to take a look, for example, the blue, yellow, and magenta. I'd love to see those almost 5, so like in a methods figure before you get to the mode or stuff. I mean, just looking at each recording site individually and then showing plots of the same from that same recording site across different fingers. So that way we can rank order which of the recording sites are giving us the most data. Right?
You had that right before.
Yeah, the rainbow square.
To show the
Oh, the rainbow square.
Yeah, but I don't want the rainbow square. I want it in temporal, just like they're showing this one. You could actually just put all the blue ones in one graph.
Oh, I see.
Oh,
And then the ones that are just envelope right on top of each other. That's just showing you the match. It's something. But I'd be curious to see if they're all. It looks to me like the red line are going to be mostly on top of each other. Maybe a slight bump for the ring.
So they're not getting much data.
Right. Maybe just cut those out.
Love that one out. Yeah. Something we can try for sure.
Yeah, right.
Then that could be a way to figure out how do we decrease the number of channels if we get down to, if we could rank order those, and just you can do it offline, right? You just try just running your own network with the 2 most influential channels. That works.
Huh. Crazy. Yeah. I like where this is going. In.
Good job.
Woo!
Excellent.
Good job, Freddie.
I want to say shout out everyone posted.
Mm-hmm. They all look fantastic.
Okay, so basically, my name is Noor, and I'm going to say what part you have. Okay.
Wow.
Next slide. That's it. Yeah. Okay, but so here's the thing. When your eye retina is stimulated by a flickering stimulus, your brain generates a wave of a similar frequency, so the same frequency or a harmonic of that frequency. And this is very cool because it opens up a bunch of applications. And I'm sure you've all heard of BCI spellers, or if you haven't, they're basically systems that use GUIs where they show different characters, so different letters that flash at particular frequencies. And depending on the frequency that's detected in the brainwave, they can tell what character someone is choosing. And that's very useful in applications where people have motor disabilities or they're unable to communicate. But here at BYB, we like to play with magic. So what we're going to do, and what I've been working on this whole summer, is designing something similar to this, in which a user or subject would pick a card using that similar working principle. And so to do that, first I developed a GUI. I initially naively went with the Rio terminal, thinking its small body would be able to flash 4 different frequencies at the same time. Unfortunately, that did not pan out that great due to induced delays. So I ended up developing a web app instead. Still has to be deployed, and it's currently malfunctioning, so I won't be showing you this at this very moment. However, it does work. And next, after developing the GUI, I wanted to test the validity of this. So does your brain actually produce this signal, and can I detect it using BYD equipment? And that's what I did. So I got a bunch of subjects. I had them stare at the GUI, and for the sake of the experiment, I was just flashing 1 card at a time, just at the beginning to make sure that I'm getting the correct signal for each frequency. And I tried with 7 different frequencies, so 4.3, 4.5, 5, 6, 6.6, 7.5, 8.75, just trying to cover the whole spectrum. Because something I noticed from previous literature is that people tend to have different responses for different frequencies. And so that's something that I also wanted to account for. And so I did this with 5 subjects. I had them look at a card for 30 seconds and then look away for 10 seconds, 10 times for each card. And we did that for every frequency, basically. And I did that with 5 subjects. And we could see that the most popular frequency was 7.5 hertz. That's the one that elicited the response with 100% of all the participants. 8.75 was also very salient, as well as 4.3, 4.5. So they varied. Most participants responded to all frequencies, missing 1 or 2. We can see at the bottom the raw EEG signals that I got for each frequency, alpha waves at the top. And then, in order to better characterize this frequency response, I plotted the PSDs of the EEG epochs, and I averaged them. So the length of the epoch was 20 seconds. And we could see that the peaks of the PSDs coincide with the frequencies that were the target frequencies. This particular PSD is for Ariana's data, where she had literally all of the frequencies on target, which is very cool to see. And then further up, I'm showing this for one frequency only, the 7.5 hertz one, also from Ariana's trial. You can see the individual traces, and you can see how they all basically coincide and go up in that peak at 7.5 hertz, which is very cool. So after that, the goal was to detect that frequency using code, be it machine learning or not machine learning. And so to do that, I had to quantify the frequency information that I have. So when trying for the machine learning model, at first I just tried inputting the raw data, but it did not give great results at all. So I opted for doing my own feature vector. And what I did is I basically used the PSD for each individual epoch, and I did this 4-element vector where each element corresponds to a target frequency, and the value of that element is the power at that frequency in the epoch. So you can see if, for example, the target frequency is 7.5 hertz, then I would expect the feature vector to have the 3rd element, which corresponds to 7.5 hertz, as the highest value. And I fed that into Edge Impulse, and I got a training accuracy of around 70%, testing accuracy of 48%, around 50%, which is greater than chance. So chance here is 25%, so it's reasonable, it's decent. But I figured that we could do better, especially because it's just a 4-element vector. It's a matter of seeing which one is greatest. So I wanted to try and see if I can hard code this and if this would give me better results. Tried doing FFTs on Arduino, it did not give great results. So then we went for something that had a much faster response and required less computational power. And that was the notch filter method. And the notch filter method was basically relied on the fact that you can determine the contribution of each frequency to the total power of the signal if you knock it out and see how that power changes. So I computed the total power of the epoch, then I knocked out the target frequency from the signal using the notch filter, and then I computed the power after that. And by subtracting this, I was able to tell the contribution of that target frequency. And I did that for all 4 target frequencies. And it worked. So I initially tried it on, so I deployed it on the Leo terminal because this is where I was doing all my processing. I deployed it there, and it did very well with inputs from the frequency generator, and it also did well with pre-recorded data that I had from the old trials. And I'm actually going to show you right here on my laptop. So I have the pre-recorded data loaded, and
the demo.
yeah.
Live demo.
Live demo.
And you can see here from
Here, it's on my
the yellow line being the highest value.
Turn around.
Oh,
Yeah,
yeah,
put this
okay.
camera on you.
Then,
People
like,
want to see. Public.
Show the people.
One second. I'm gonna restart this just to this is the frequency, like it's like full live data, right?
Yeah.
And this is the kernel. So this is loaded with previously recorded data. And this is actually Freddy. Don't point the camera at my face. This is Freddy looking at the card, flashing at 8.75 hertz, right? And which corresponds to this card. So now when I reset this, it's supposed to show this card being circled because that's the card that Freddy was looking at the time. And I'm also here going to show you the serial plotter, which will show you the notch vectors, the elements of the notch vector. So, that's the serial plotter. And you can see how it selected this card.
Wow.
Yeah, and here on the notch, exactly. That's the cool thing about the notch filter method. It's very fast. And you can see here how the yellow line is the one that has the highest amplitude because that's the one that corresponds to 8.75. So it works. And I guess the next step is to basically get this to work live. I tried getting it to work yesterday, but there were some different errors. But it's something I've definitely been exploring for the next few weeks.
But they're hardware stuff, right? It's not like
it's just hardware stuff. Yeah. So it works, and the goal is to get it to work live. And I also want to see if I can deploy the machine learning model also, just to have some kind of comparative analysis on the actual deployed model. But yeah, basically that's it. I guess the card.
Nice.
Good job.
so
Did you do it with all the cards flashing on the screen, or did you do that?
That's also part
two.
of that's phase 2. And so the GUI is ready for that. I have all cards flashing on the screen, just in the oscilloscope and everything. Yeah,
Just to see how that affects it.
Yeah.
Very cool.
Excellent.
Lance.
Oh, is it plants? Should we do Sam first and then plants?
First.
Yeah.
That's cool.
Morning, everybody. My project was all about free will and looking into the signals that go along with free will. And there is a lot of background to say that we should be able to find these signals, but just to give you a little bit of guidance as to where this will go, we're not as excited about our replication as we might have been, as you can see from the far right side, but we'll get there. We'll walk through the process as to how we try to replicate these signals related to free will. So starting on the upper left side, what you see there is a cross-section of the brain. You have what is a representation of some activity going on in the left hemisphere of the motor cortex. So when that activity occurs, when there's electrical activity in that part of the brain, that's when you're going to have your right arm move. So basically what you should take away from that is just that we have some understanding that electricity is related to the initiation of movements. So that's one of the first things that gave people indications that maybe the electricity in the brain would be an interesting thing to study in order to understand free will. So what exactly is free will? Does anybody want to offer a definition of free will? Does anybody?
When you decide what you want to do.
That's a good way to put it. So Nora used the word decision. So to decide what you want to do. When you use your free will, you are using your own internal abilities in order to choose between two things. And one simple example of that is when you choose to move. So this could be when you choose to pick up your foot, when you choose to scratch your nose, or it could just be when you choose to flex your wrist. So for the purpose of experimentation, we were looking at wrist flexes. You can see that on the bottom left image. But just above that image, you can see a drawing that I did just to try to give you an idea of what the signals that are related to movements look like, and specifically how they differ when you have free will involved versus when you don't. So what you see is a vertical dashed line indicating the time of movement. And on the bottom line, there's a big flash that just says move. And all that should indicate to you is that there is a prompt on the bottom line and there's no prompt on the top line. The top line, what you see is a ramp in the signal before the line representing movement. And that is specifically related to free will. That's the word for the number. And there's some debate about this, But there is a lot of scientific evidence to say that we should be able to see a signal that ramps up when we're looking at a free will based movement as opposed to a prompted movement. So on the bottom left there is my buddy Sachin wearing a really cool neuroscience hat. So shout out to Sachin. Thank you to everybody who let me put gel on your head this summer. Appreciate that. But then moving on to the middle of the poster, what you can see there are 3 different electrode configurations. At the top we have C3, and then we have C3 versus C4, and then at the bottom we have CZ. So C3 is going to be the electrode that is right over that activity you see in the top left corner. It's on the motor cortex and slightly to the left of the midline. And then C3 versus C4 is going to be taking the electrode that's placed just to the left of the midline and subtracting it from the activity of the electrode that's placed just to the right of the midline. And then on the bottom you'll have CZ, which is just right on the midline. So what I plotted here are 730 trials pulled from sessions using the BYB equipment and OpenBCI equipment.
How many sessions?
14. Yeah. And so, and what you can see is that in C3, we see a shape like the readiness potential, like the drawing that I have on the left side. In C3 versus C4, we don't necessarily see that. And the same in CZ. And basically, this is just to illustrate to you some of the struggles that we've had with finding this signal. Literature tells us that each of these electrode positions should be able to pick up some kind of readiness potential, and that it should be more and more obvious with more trials. But as you can see from these traces, we are getting a lot of we're getting a lot of either noise or just not necessarily getting the signal. And these again are the cleanest trials from the cleanest sessions from the whole summer. Yeah, so this was a difficult signal to replicate. It doesn't mean that it's necessarily not possible to replicate, but I think that in the future, if we are going to replicate this, it may take much more careful attention to how to filter out noise artifacts, and not just electrical noise artifacts, but artifacts related to internal biosignals. Yeah, so that's the center graph. And then if you move on to the upper right, I have an example of one graph where, or one session where I actually did find a very clean looking readiness potential in the average. Yeah. You know, I don't get to say those words. But here we are. What you can see as, first of all, the vertical lines represent different times. So the red vertical line shows you when movement onset is. And that's important because that should be exactly where the peak of the readiness potential should be. Right after movement onset, that's when we would expect a big dip in the EEG signal. And right before, if it's a free will based action, that's when we expect that ramp. And as you can see, that ramp actually goes from inside of 95% confidence intervals to outside of it at about the 550 millisecond point. And actually, that's a significant finding because that's actually what some of the original papers related to the readiness potential found from Dr. Hornbuer and Dr. Wyden. And so, yeah, it even has a similar time course to what we would expect from the literature, which is reassuring. And then lastly, one of the things that was very, it was a difficult fact to ignore, that throughout the summer, I reported lots and lots and lots of sessions. There were lots of reasons why sessions were good or bad, but all in all, I reported over 50 sessions that had failed replications and only 2 that had successful replications. And I don't feel that I can say conclusively whether or not this is has been properly replicated, but I think that we do have at least some indication that this signal is very difficult to replicate, very difficult to find in single trials. Single sessions. Yeah.
Yeah.
I'd be surprised if you did that C3 by session that you don't. I mean, it's so clear in the average of 14 sessions that you wouldn't see that in many of the. Have we gone through and actually verified that the C3 isn't working?
Yeah, no, that's we've been presenting those averages like every single like daily slide, and the thing that I'm reporting there is just that we're not breaking the confidence interval. But I think you are right that the C3 does have that shape of that readiness potential. But what I was considering successful replication was crossing that 95%.
For no session across in this case, or
No. We had 2 successful replications total.
Yeah,
This is the one I'm trying to talk about.
the 2 successful replications was once with Sachin and once with your own data. And in the middle you have 12 sessions from Sachin.
14 sessions from multiple different subjects.
Multiple different subjects.
Yeah, multiple different electoral positions.
Including your own readiness potential, so it contains the 2 successful repetitions. But
And that's a
and all the other 12 sessions didn't exhibit it didn't cross it. But, okay.
I think that they all didn't really cross it, but averaging them together kind of boosted that, and plus the sessions that actually worked kind of helped.
But only on C3.
Yeah, only on C3. So, but C3 looks better. So CZ is good because of that sharp drop. It doesn't really ramp up, but the drop is what gives it away.
And
But again, this isn't conclusive.
From
If we're more directly confronting some of the noise problems and some of the internal issues, one of the things that was so difficult to get right with this was just I found there were often artifacts related to just when the person would move because the electrodes would shift around. That was a really common one. I think those are just important things that have to be addressed head on.
so you did some kind of pre-evaluation of the recordings, and then they took out of these 50 plus 14 that you were sure that.
Yes.
But is this is it kind of crossing the confidence interval?
I'm not sure on C3. I haven't thought of that. I haven't made the functionality to work with making Monte Carlo averages from all 14 sessions separately. I was working on this until 8 a.m. Wow. But yeah, so.
Yeah.
No, I'd be surprised if that doesn't. I mean, just, I don't know, it isn't zoomed in, but
Yeah.
the
The middle part is nice.
The noise. Are the noises similar across all 3 of those?
Yes. Yeah, and the thing is, it's also 730, so there were a lot of different examples of noise in each of the different trials.
Yep.
Makes sense. Do you think showing the other traces would be better because that's just corners?
Like the 730 behind each of them. Is that what you mean?
Yeah, but super light.
Yeah.
Super light.
That might have to be really light.
But what about the ones on the right?
Yeah, so I think we do. It is helpful. We still see a lot of a large amount of variation across them. One of the things that's difficult is these 95% confidence intervals are related to the average, and not necessarily related to the raw traces. So even if this is crossing 95% confidence intervals there, it doesn't necessarily mean that it is on a raw trace, for just a single movement.
So thinking, I don't know, continuing this work for maybe a year or something like that, do you think it would be at some point possible to have a single trial detection?
Yes, I do. And I think an important feature of how to do it is one of the things I keep seeing pop up in the literature is a correlation of a specific function to a window of time. And by fine-tuning that function, they're able to, I think they even modify it and personalize it based on training data. But I think that method of correlating a very small function to a very small window of time, I think that method is actually very good. And then also doing some component analysis so that one of the things that would be present in your components would be the readiness potential, and then matching it to that correlated function. That seems to be a really good way of approaching this.
So you could get a slash predictor maybe?
Maybe. Yeah, the search continues.
You know what free will is? Free will is you choosing to name everyone in the fellowship but me.
I noticed that too.
He said, I don't need your videos for like demos, so
I'm so sorry.
screw you. Delete. No, it's fine. I was like, oh, that's supposed to be named all of us, and I got to credit.
No,
I was
he
like,
didn't.
Oh.
I really did.
No, that's okay. No, that's
But great effort.
white whale.
You got it? Caught it?
Yeah.
Thought about it.
Rain on it.
One more.
Plants.
Okay, plans. Yes. No, yesterday we had the
Maybe someone who's closer to it.
All right, let's see.
all right.
Can you guys hear us, Chris?
Perfect timing.
It's such like an asshole scientist move. Oh, wait, it's watching this? Perfect timing.
Actually, the worst is when you're first, then you just leave.
Oh yeah, you're right. No, but I'm gonna do the Tim because I prepared the slide and I'll let you talk, but I'll first like give you an introduction of how I produced the slide. So I was really like literally getting all the individual trials where it worked for the 3 different plans. And yesterday I was at the Mental Shrimp Dan Upward Bound High School summer school, and they were as a science communication exercise doing a emoji like talk summary.
Oh, right.
And we see that in the middle, and I'll just like.
All right, so Tim, take it away. What's it say?
What does it say?
Okay, so we should implement this. I mean, I love this idea. So there's me without a beard but with a mustache, as a scientist, and then we have an alien, which is E.T. Okay, and then the past 2 weeks we've been doing exploratory.
Now this is clear.
The plant was the alien. Like, what is this thing on Earth? You know,
The plant comes and he sees people walking around in slow time and organisms walking around in slower time. He's trying to figure out which one is smarter. And so then we use the fire on a number of plants. So you can see 3 types of plants there. There's a moving plant. It looks like it's moving, so that's mimosa. Then the other generic plant, I think, represents the Drosera, and then, of course, the tomato. And then you can see with the fire, with the 3 plants, we measured the electricity. And so what does that mean? That we did see the electricity.
This is so good.
Yeah, that the plant is alarmed, and it's like preparing its defenses against future attack. So that's how you can explain the research in emoji. And we would like a $2 million 2-year grant. Please, government of the world. It could be Germany. It could be Asia. The only failure is that we weren't able to figure out how to measure the speed, the conduction velocity. So that's it. If I were criticizing myself, which. Like that's where we failed with the data. So what's cool about this is that this is almost all our data. So actually, Greg, if Etienne and I were hit by a car today, Greg could take this data and say like, this is the last. All the
Memorial Award.
So we use the flame stimulus, and so these are the 3 plants. So what plant is this?
Drosera.
The Drosera. What plant is this?
Tomato.
And it's not dead. It is slowly.
Nice.
I have to water it back to life.
Sonia is happy with us. And then what is this?
Mimosa.
So these are so in the Drosera and the tomato we have responses to the flame stimulus. And mimosa, what's the stimulus? Touching it with a plastic or glass probe. But what really gets Greg excited, what gets me excited, gets Etienne excited about kind of the future of backyard brains with this plant stuff is we've had a breakthrough. Does anybody know what the breakthrough was?
Oh, the double
Quantification, measuring the conduction velocity. And so I'll let ETR explain this part.
Okay. Yes. So we used artificially. We were mimicking kind of like the stimulation. I think for Drosera, it's normally the fly is landing on the tentacle, eliciting the signals, and then it slowly curls up to digest the fly. In a tomato, I think it's a herbivore response. It's called the wound response. And we mimicked these responses or kind of boosted the responses through setting the plants on fire. So every time on every trial, we see the time point where we set the plant on fire with the event marker. And then we have the recording on the two sides on the branch. And we see in the channels a delay of the action potential. And we can calculate the conduction velocity by measuring the distance between the two electrodes and the difference between the peak of the two electrical signals. So we did that for every individual experiment. For the Drosera, we're in a range of 2 millimeters per second, how the signal travels. For the tomato, we're between 4 and 15 or 16 millimeters per second, but it's the same order of magnitude. And for the mimosa, we're also around that range. It's about like 8 to 15 millimeters per second.
And if you don't live and breathe conduction velocity, maybe some of you know, what is the speed of the alpha sensory fibers and the motor fibers in your arms and legs? Does anybody know off the top of their head? We think about this stuff all the time.
Way faster?
How much faster? How many times do you have to move that decimal place?
One.
A couple of times. It's 50 to 80 meters per second in your body, and that's why mammals move a lot faster than plants.
What is that miles per hour?
That's like 200. I think it's like 190 to 250. So like I make the analogy like super fast race cars is the scale of the fastest fibers in your body. It's like Formula One type stuff. And then in the earthworm, the squid, does anybody know how fast that is? About 10 meters per second, 10 to 15, which is bicycle speed. Like if you're really kicking it on a bicycle, you can go that fast.
4.1 millimeters, that's like a kid just barely moving the car.
It's like an ant.
It's like an ant is good. Yeah.
So the disappreciating thing is things being farther away, like each different. Oh no, or this is over time. You keep doing it. What is this bottom one?
This bottom one?
No,
The bottom.
Right. Bottom.
Yes. Yes. So here, these are like the special experiments, let's say, where we have all these open questions coming from.
Yeah.
So here we have tapping it multiple times.
The same area.
The same area in the middle of the branch between the two electrodes. So we don't have to look at the difference of the signal, but just like with multiple tapping, the signal gets weaker and weaker and weaker. Then we have these kind of inverse signals sometimes, so that we have a positive deflection in one channel and a negative one in the other. We see that also for the mimosa especially. And we have signals that might be only the signals when the leaves are closing. So the mimosa has like the closing leaf reaction, but at the same time also the dropping the branch reaction. And having these very fast signals with around like 40 millimeters per second, maybe these are just for the closing the leaf, and then they all have to add up to create or generate these huge action potentials, because the signal was also stronger, or so strong that it was actually already doing clipping in this bike recording. So maybe these are kind of like several electrical signals generated differently, and then they kind of at some point come together and create that huge action potential that then lets the whole branch like fall down. So that's something that we just have to investigate with multiple channels on like multiple recordings on the same plant. And then I think it's possible to figure out the mechanism for that response.
That flipping signal is real, or is it some artifact?
That's the filters. It's not single plant stuff. It's really out of control.
But it's weird that it would be synchronized so closely, because if you I suspect if you moved,
it's not exactly aligned. We could check.
Okay, but so if you move the second electrode to further down, then you could actually get it. You could actually shift those in time, then, so the red would come way after.
If we find a very long branch, yeah.
Yeah.
I think these are most of the times already the longest branches, and then also with because they have to kind of withstand also the hooks of the electrodes, and if they see that already as a stimulus, then they fall down already. So with the mimosa experiments, you have to be quite careful to not kind of bring them in the state of.
Yeah, the mimosa is actually the trickier plant to work with.
Yep. Yeah, for the Drosera and the tomatoes, I think you've seen it in one of the stand-ups. It's a setup of 10 minutes.
Mm-hmm.
Just hook up the branch or the tentacle, set it on fire, and you see it. And for a tomato, it seems like it's only working kind of once. So maybe once the wound response enters the whole plant, there's no need for a second one. So yeah, that's the.
Or the second one's on the time scale of the tomato plant, which is.
This is like way down the line, but I'd be excited to see something like a genetic knockout of this response.
Yes.
That would be incredible.
Yes.
Yeah, we actually ordered Arabidopsis seeds.
Really?
They haven't arrived yet, so that's the idea, that we can grow some Arabidopsis and see it. And if we can get a protocol on Arabidopsis, then we have access to all that genetic stuff.
Yeah, yeah.
Yes.
And if we were really pushing for it with CRISPR-Cas9, could also be possible to knock it out in tomato plants. So
Yeah, that'd be awesome.
I really want to see what happens if you burn the fruit.
yeah. So in general, to like give it more like this bigger picture is that first of all, we can now measure the velocity, conduction velocity in another organism or another kingdom, actually. But it's more about also the question, why? Why are there electrical signals? So that we just like kind of ask us the questions, at which point do we have to move from solely chemical information transmission to electrical, and that even plants are doing it. There might be just like a reason behind it, that at some point we need electricity because it's just a bit faster. And then we have different techniques or different mechanisms over all different kingdoms that they implemented in their response properties to kind of react to environmental changes.
We're just overgrown plants.
And what's cool is that this is the first result that the Drosera, the Mimosa, and the Venus flytrap can be considered exotic plants. So you can kind of do the hand wavy thing, like they have electrical signals, but they're like the weird moving plants. But the tomato, man, there's nothing exotic about a tomato.
Yeah.
Except that it tastes good, you know.
Exactly.
Awesome.
Very fun. Very cool. Future DID.
All right. Any comments from the virtual world?
Anyone have their volume?
The volume.
So.
I think we're good.
Okay.
Yeah. You know, the inspiration is just running through the veins.
Yeah.
Then, thanks a lot for the last stand-up.
Weeks.
Thank y'all so much. It's been like
perfect.
Are you keeping your
experience of a
title
lifetime.
on your poster? Are you keeping your title?
Yeah, I like it. if I should change it, we can talk about it.
Yeah, no, I think we can maybe do some last modifications.
Yeah, right. So I meet with people one-on-one. I think we're going to go through some other suggestions.
Printouts, and then
When's the busking?
Came in.
yes.
What's this? That's for
Tattooing.
That's the
Yeah.
Okay.
So we're getting people to agree to dots behind their ear, and that's what we're trying to get everyone to do at least.
Yes.
The symbolic EEG dot. The drum sample. That's
yeah,
where
the
I
mastoid. Yep, that's where the ground,
dot EEG.
where the ground is.
Classify on
And
that.
you never see the tattoo anyway because you always have the
Yeah.
attach electrode on there. So
But it's actually just a marker of where to put it, so you know, like where's the ideal ground. Find out.
You're another kid in the back.
So now
Oh, probably not.
you're like, oh yeah, right there. And they're like, oh.
I actually did all the math. This is my ideal ground placement for my knife. So put it right ideal.